concept, and I've been involved in the community in a number of ways over the years. Was out for a few years, came back last year. I'm currently serving on the CI team and also helping maintain Plone REST API, Volto, doing PR reviews on different things. So let's talk about deploying in production. What do I mean by production? Well, I mean that we're serving public traffic. Well, if it's an internet, maybe it's not public, but we're serving traffic for the intended audience of the site, at whatever capacity it needs to be. So it needs to be highly available. We don't want the site to be going down. I'm going to talk about different maintenance tasks that we need to do over time to ensure that the site is not going to die because we ran out of disk space or whatever. And along with that, some of the monitoring considerations, things that we need to look out for. I'm going to show you the setup that we've been working with for a site called dlr.de. It's the website for the German Air and Space Agency. Timo is going to do a case study on it tomorrow if you want to learn about the features of the site for the actual editors and end users, but I will talk about the deployment. Also, I have to give credit. A lot of this is stuff I've been working on, but also Eriko has done a lot of work on it. Fred has been involved in the past few weeks or months. And then, of course, the whole Kit concept team has been building the site. It's actually what I would call a medium-sized Plone site. I know there's deployments out there that are much larger than this, running hundreds of websites. This is just one website. It gets about 15 million hits a month, which is, 5 a second. It's not outrageous. The website has or will have multiple subsites, so there are quite a few editors who will be working on it, different groups of people editing their own area of the site. And one of the things that's unique about this particular client is that they needed to deploy in their own private data centers. So we can't just go get components from Amazon, pay for Datadog for monitoring, et cetera, et cetera. We actually have to do it ourselves. So I'll give a quick overview of how the system looks, and then I'll get into some of the details. So the basic idea is we have 2 zones. So think of these as different data centers. Maybe each zone has, in our case, it's multiple VMs. Maybe for a smaller site, it's just 1 VM in each zone. But we want to have each service running in 2 different places so that if one of the zones loses its connection to the internet, we can still serve the site from the other zone. Traffic from the internet comes to the front end, and each of these different colors is a different, I'm going to call it a stack because that's what it ends up being in Docker Swarm. It's a piece of the system that we can deploy at once, but one stack is going to contain maybe multiple services, definitely multiple replicas of those services. So the green stack is the web stack or the front end stack. It has traffic as a load balancer and varnish as a cache. The traffic from the internet is going to look up where to go in DNS. It's going to get the IP address of one or the other of our front-end machines and start there. Then we've got an app tier, which is Plone the front end, Volto the front end, Plone the back end, all running in there, scaled out horizontally to a number of different containers, enough to handle the traffic that we're getting. The apps are connecting to a database, which is ZODB using rel storage with Postgres. So we have a primary database server, which is handling this most of the time. We are working on adding a replica that will be a failover in case the primary database goes down. And then we have Solar for search. So this is somewhat complicated. There's a lot of moving parts that you tend to get to this point pretty quickly in any Plone deployment. How do we manage them? We're using Docker Swarm. It's not the only way to do it. I know people are using Kubernetes. The sort of way we did things traditionally was use a tool like Ansible to just set up a bunch of hosts with the things you need. But Docker Swarm is what we're using here because it provided a good way to manage services across a number of different machines without all of the complexity of running our own Kubernetes cluster, since we can't use EKS or other cloud-based services. Even if you're not using Docker Swarm, I think a lot of the things in this talk will still be considerations that you need to think about when you're hosting Plone. So even if the specific solutions aren't relevant to you, these are still things that you need to think about. But let me tell you a couple of things that I do like about Docker Swarm, even though they are traits that you can get elsewhere as well. It's containerized. So what I mean by that is we build an image somewhere, CI, maybe locally, and then we can deploy that image to multiple machines. So it's not like build out where we have to do the build process on each machine that we're installing to. And this is just good for consistency. You only build the thing once, you can test it, and then know that you're getting the same thing in each place. So even if you've only got one server as your target deployment target for where you're deploying, it's still, I think, a good idea, because then you can run your development machine the same way. You can run your CI the same way. The other thing I like about having containerized apps is it's consistent across different software stacks. So if I'm deploying Solar, which is written in Java, or if I'm deploying Plone, I can configure it the same way. I just need to say, I want to run a service with this image, maybe run this command, give it these environment variables. It all looks pretty similar regardless of who built the thing in the first place. Docker Swarm takes care of process management, and this is just the basic stuff, like if a process dies, I want it to start back up again. If we're running low on memory, then I need to kill off the process before it gets killed off by the kernel, that sort of thing. Docker Swarm is similar to Supervisor D, the tool that we used years ago that was written by Chris McDonough in this regard, except that it can also handle processes across multiple machines. So if the process dies on this machine, maybe it'll get started up on this other one instead. So if this machine goes down entirely, we're still good. Docker Swarm handles rolling deployments. So when I want to update something, I build a new image, I tell Docker Swarm, hey, go deploy this existing service, but with the new version of this image. And say this is like a Plone backend, so we've got maybe 4 different replicas. Docker Swarm will take down one, bring it back up, wait until that's receiving traffic, then it will take down the next one. So for the end user who's hitting the site, they don't see any interruptions. Docker Swarm handles a number of things with the network for us. The dark section at the bottom here is an internal network, and the top section, the traffic from the internet to the load balancer, is a separate network that's public. So Docker Swarm gives us the ability to create what they call overlay networks, so you can sort of isolate your traffic without needing to think about the details of firewall rules. Also, all the traffic going through the Docker network is automatically encrypted without us needing to do anything special. And finally, Docker takes care of DNS for our services. So when Volto is connecting to the backend, we can just say, hey, connect to http://backend, and we know that that will get routed to whatever IP addresses are currently serving the backend at that time. A key thing, I think, these days, whether you're using Docker Swarm or not, is to think about having declarative infrastructure or infrastructure as code. So you want to have your system defined in files. So this is a YAML file with Docker Swarm configuration. This means we write it, it gets checked into version control, it can get reviewed by somebody, we can look at the Git history and see what changed when. So it makes it a lot easier to keep track of what's changing in your system. You can see here the whole file here is for one stack, which is the app stack, and then it has multiple services, front end and back end. Each service has the image that it's going to run, some environment variables, some deployment configuration, how many replicas we want, if there's any constraints about which VMs it can run on, that sort of thing. Once we have this configuration, we just have to run this command, docker stack deploy, the app.yaml configuration to become the app stack. And you can run this manually, or you can set up a CI process that will do this whenever you commit changes to the stack. All right, so that's Docker Swarm and why we're using it. Next section, I'm going to talk about how do you actually keep a service up as a highly available service. The conventional wisdom, or most important principle here, is to avoid single points of failure, right? You don't want to have any single thing that if it goes down will take out the system or stop things from happening. This principle is fine, but the thing I don't like about it is that it makes it sound like failure is a rare, unexpected condition. So in fact, I think actually failure happens all the time, and you want to be planning your system knowing how each thing can fail. And by fail, I mean we're going to need to install operating system updates, so we need to restart the VM. We're going to need to deploy updates to a service, so we're going to need to do a rolling deployment. So for each service that's running, we need to think about what happens when it's down temporarily. This is easiest to do for services that are stateless. By stateless, I mean it's not storing anything locally. It's just receiving traffic, doing some processing, maybe getting some things from another service. But if it needs to restart, it just dies. We start up another one. It continues receiving requests like it was before. In a Plone deployment, this includes the app servers, so Zope and Volto, the databases somewhere else, and the load balancers. Stateless services are also the easiest thing to scale out horizontally. You can just add more as you need them. The main nuances to think about with stateless services are when you need to restart one for deploying an update or something, you have to give it a chance to shut down cleanly, right? You don't want to interrupt any request that's currently happening. So you need some way to make sure that it's given a chance to gracefully shut down and stop listening for new traffic. And the other consideration is if the stateless service is connecting to something else and that something else goes down, it needs to gracefully handle that failure in the connection and try again. So a little bit harder situation to deal with is using Varnish as a proxy cache. So requests are coming in, responses are coming back, Varnish is storing them. I said store, so it's not stateless. And in particular, the problem that we had with Varnish is when something changes in Plone, you save and edit to a page, we want to maybe send a purge to Varnish to say, hey, whatever you've cached for this, make sure you invalidate that and we'll get it fresh next time. Now, we have 2 copies of Varnish, right? 2 replicas, because if one goes down, we want to have the other one. So that means we need to send the purge to 2 different places. Well, Plone has a way to do that. You can configure multiple host names in the caching control panel for where to purge things. But in Docker Swarm, both of these have the same host name, right? It's just http://varnish, say. And that resolves to multiple IP addresses. So we have a solution for this. I'm not sure it's the right long-term solution, but it's working for now. Eriko made a thing called the cluster purger. It's a little fast API application. So Plone sends the purge request to the cluster purger. The cluster purger looks up the current IP addresses of Varnish in DNS and then sends the purge to all of them. Databases and other stateful services are also more complicated. We can't just take the database down on this machine and start it up on another one because it won't have access to the data that it's storing. We can't allow writes to happen on multiple replicas of the database because then things will get inconsistent. So we use this pattern with a primary database replica and a standby. And this is a pattern where there are tools for it in Postgres. Postgres has built-in support for doing streaming replication where you can say, anything that's happening here, copy it over there. There's also some tools out there for handling the load balancing and failover. So recognizing, wait, this database is down, we need to send traffic over here instead. A particular one I've heard mentioned a lot is called Plone. We're actually still in the process of setting this up for this deployment, so I can't necessarily speak to a lot of the details, but this is the direction we're going. For high availability, you also have to think about what happens if there's a network connection problem. So this is one scenario that's pretty simple, and then I'll show another one. In this scenario, zone 2 has lost its connection from the internet. But the internet can still connect to zone 1, and all the traffic between the two zones is still working fine. This is a pretty simple situation, right? The traffic is still reaching the cluster is still operating fine. Things are not really going to stop working. This one is harder though, and this is a situation called a split brain where the two zones of the cluster can't talk to each other anymore. And the problem here is the traffic that's coming from the internet to zone 2 is going to hit app servers that don't have access to the primary database, right? So any traffic that gets there is not going to be able, we're not going to be able to serve a response correctly. How do we want to resolve this situation? Well, maybe the answer is we just shut down everything in zone 2, right? Then all the traffic goes to zone 1, gets served from the primary database. Good. But that's assuming that zone 1 is still receiving traffic from the internet. If we also had a red line above zone 1 and the internet wasn't reaching zone 1, then really we don't want to shut down zone 2. We want to keep it going because it's the only thing that's left. And the problem is that from zone 2's perspective, it doesn't know which situation zone 1 is in because it can't communicate. So how do we resolve this? We need some other mechanism to decide which of the zones should become the primary one in the failover situation. I could say a lot about raft consensus algorithms and how all this works, but what you need to know is there's pieces of the system that are sending messages to each other, always trying to keep track of what's up and who should be making the decisions about where things are running. We have this in Docker Swarm. It has a piece called the manager, which is doing this. If you're using Plone for the high availability of the database, that is also doing this sort of thing. The key thing you need to know is that you need one more manager than you have availability zones for your application. That way, if one of the availability zones becomes unavailable, the two remaining managers can talk to each other, realize they have a quorum, and decide, okay, we're going to keep running here. And in the zone that has lost its connection to the internet, it realizes, oh, I'm just one, I need to shut things down and not cause problems. Final minor point for availability, think about your resources that you're using, CPU, RAM, network bandwidth. Docker has ways to configure limits for a particular service. So you can say, this machine has 4 gigabytes, but I don't want this service to use more than 2. If you don't set those, then you might use up all the RAM on the machine, and then the kernel is going to kill something off, and maybe the thing it kills off is Docker itself, and then you can't start things back up. So think a little bit about what limits you need to enforce. Okay, so we know some of the things we need to think about in order to get high availability. Let's talk now about what processes we need to be running over time to maintain the system. There's some variables that we're going to want to tune just to make sure that things are using the resources as efficiently as possible. We are using rel storage. We are storing our blobs in Postgres. This is not the only way to do it. You can also put them on the file system. But because we have a number of different machines, keeping them in Postgres is an easy way to make sure that they're available from everywhere. When the backend retrieves blobs from the database, it caches them. And there's a variable called rel storage blob cache size, which determines how many or how much data can be stored locally where the backend is, so that if the same blob is being fetched a lot, it doesn't have to get it from the database every time. I think the default in the Plone backend image is fairly low, like 10 or 100 megabytes, I forget. So we set it a little bit higher. We're also changing the ZODB cache size, which is how many objects can be stored in the ZODB cache. This has a big impact on how much RAM your backends use. It also has a big impact on performance, because if you're doing a catalog query and you have to fetch all these indexes from the ZODB, if you have them locally in the cache, it's going to be a lot faster than if you're having to get it from Postgres. Setting the right value here is a little bit of an art. You can look in the ZMI to see how many objects are falling out of the cache. I think that's still available. Don't remember for sure. But in any case, you might want to play around with different values here and see how it affects performance. We also have some things to tune at the Postgres level. And this is a whole bunch of configuration that I don't necessarily need to talk about all the details. But a lot of these settings have to do with how much memory Postgres is allowed to use for different operations. So the basic relationship is the more memory you give it, the faster things can happen in some cases if you're doing an operation that's processing a lot of data. So think about how much memory you have on your machine and make sure that you're actually giving Postgres access to it. The shared buffers I've set to 4 gigabytes. This is going to use shared memory from the operating system. And there's a related section down here where I've mounted a temporary FS volume with that much space. That was to solve a problem where we were getting errors because Postgres was trying to use more shared memory than Docker was giving it. So those two go together. The max locks per transaction is another one to pay attention to. If you're using rel storage and you're doing an operation that touches a lot of objects, like moving a very large folder from one part of the site to another, well, for one thing, it's going to take a while just because of what needs to happen. But another thing is you might get an error that actually it couldn't complete the operation because it ran out of, I think it says something about locks in the error message. This is the solution to that. Postgres has a limit on how many objects can be locked. It's this number times the number of connections that are allowed to Postgres. So if you hit that error, you might need to increase the max locks per transaction. Let's talk about backups and packing, which are processes that you need to run from time to time on your site. In a classic deployment with Ansible, we would have just set up a cron job with a schedule to do the backup once a day or something and do the packing once a week or something. In Docker Swarm, we don't know, we have many VMs and we don't care which VM the process runs on, but we do still want to run it on a schedule. The way that we do this is we set up a cron service using the Crazy Max Swarm cron job image, which is basically going to run cron, but inside Docker Swarm. And it will take care of spinning up some other services that I'll show you in a minute. In order to do that, we need to give it access to the Docker socket, so that's what that volume mount is. And then I'm setting environment variable with the time zone, just so that we're starting things at the correct time. So now we have a backup service that is going to be scheduled to run once a day using the swarm cron job mechanism. So this one is a service using the Postgres image because we're actually going to run the Postgres pgdump command. Postgres has several different ways to do backups. You can decide which one works best, but that's what we're using. So we have this image. We have a script that we're going to run. The script is added as a Docker config, so this will make it available within the running container. We're constraining the placement of this, so it'll run on the specific machine that the primary database is on. That's just for performance reasons, so that it's close to the data that's being backed up. we're running 0 replicas. That means that unlike most of the services in the Docker Swarm, this one is not going to run anything most of the time. It's only going to get run when it's started up as the Swarm cron job. We give it some labels, and these labels, the Swarm cron job process is going to look for on all the Docker containers that are running, the ones that have these labels, it knows, oh, this is the schedule, I'll start it up at the right time, and I'll make sure that there's just one running. And we're setting restart policy to none so that unlike normal services where if it goes down, you want it to get started back up. In this case, actually, we just want it to run until it's done and then stop. The volume mount here is actually mounting the location on the host machine where we want to write the backup to. So packing the database is another similar operation that needs to be run from time to time. In the ZODB, whenever we make a new transaction, it's actually adding data. Even if you deleted an object, it's adding data that there was a new transaction that updated that object. The only time the old data is removed is when you do a pack, which finds the old transactions that are not needed anymore. When you're using rel storage, this is also needed, just the same, if you have history turned on. You can turn history off in rel storage, but then you lose the ability to look at the undo log and see the transactions that have happened recently, which is pretty useful. So we have history on, and we're running a pack job from time to time. So like the last one, we have labels to set this up as a Swarm cron job that runs once a day. It's not going to restart. We've got 0 replicas until it gets started as a cron job. This one is using the Plone backend image, which is maybe a little weird. We're not going to try to run ZOP. But the reason we're using the Plone backend image is because it contains the ZODB pack command, which is what we need to run. So we're using that image, but we're using not the default command. We give it a configuration file, which I'll show you in a second. We give it the information it needs to connect to Postgres, and we turn off the health check for the backend container because normally the Plone backend container has a health check. If you run a service with this image, it needs to pass the health check before it's considered up by Docker. But since we're not actually running ZOP in this case, we don't want to check the normal health check. You can see there's a couple workarounds here. I think we can make this a little bit cleaner if we created a special image just for doing the packing. So maybe that's a sprint task. This is the configuration file I mentioned. It's very simple. It's just taking the rel storage DSN environment variable that we set up before and putting it into the file that the command accepts. So you'd hope that that would be enough to get rid of our old data, but no. Postgres has a thing you need to do called vacuuming. When we store data in a Postgres table, it allocates some space from the operating system that it can use for data, and it doesn't give that back until you vacuum. In fact, even when you vacuum, it might not give it back to the operating system, but it will at least keep track of what parts of the disk can be reused to store new data. Now, vacuuming in Postgres happens automatically, fortunately. The thing I wanted to mention about it is that it kicks in automatically after a certain percentage of the table has changed. I think it's maybe 25%. So if you have a very large table and you're changing it a lot, it still might not get vacuumed until many changes have happened. And in our case, we've got a table with the blobs. Most of them are not changing that often. So that table is not getting vacuumed automatically by default. There are some settings for Postgres that you can use to tune this. So you can say, I want it to auto vacuum after 10% of the table has changed instead of 25%. So look those up if you have a situation like this. Another sort of maintenance that we have to do is operating system updates. Docker Swarm makes this relatively straightforward. We can tell it we want to restart this particular node in the swarm. So drain that node, stop running all services on that. Docker will take care of starting them up on a different node. Then we can do our restarts, update any packages that we need at the operating system level, and then re-add the node to the swarm. Of course, it's a little bit more complicated when you're dealing with stateful services like the primary database, and then you need to either plan for downtime or do a failover sort of situation. And the last thing I wanted to mention about maintenance is when you need to run scripts. So like the sort of script that you would run with bin instance run. It's a little bit more complicated when you're in Docker because you have to go through a couple layers to get there. So you SSH to the host machine, you run docker ps, look up the container ID, you run docker exec with that container ID and run bash, so that gives you a prompt inside the container, the backend container. And then you can run docker entry point.sh run and the path to the script. It's a little bit annoying, but at least you can get there. The last section I've got here is about monitoring. This is important just so that you know what's going on and can catch problems before they become critical. You want to be proactive and think about what situations you need to be aware of. Do I need to monitor disk usage? Do I need to monitor how much traffic is hitting the system? What situations do I want to have alerts for? There's a word that gets used these days called observability. You want to build a system where you can easily get the information about the system that you need because it's been set up from the start to observe that information, and you're not trying to go back after something happened and find data that hasn't been recorded. The most basic type of monitoring that you probably want, even for a small Plone site, is the site up. And for this, you want something that's running outside any of the data centers that are under your control. If the network goes down to everything that you're in charge of, you want to find out about that. So there's a number of tools out there for this, things like Pingdom, Uptime Robot. They're pretty simple and easy to set up, not too expensive. Find one of those and use it. The other point about this is we set this up, and then we had an outage, and we didn't get an alert from Uptime Robot because it was configured to hit the front end of the website. The front end of the website was loading, and it was returning fine. Why? Because it said server unavailable, but we were checking for the title of the website, which is just a static piece of Volto. It wasn't checking for anything that was coming from the database. So think a little bit about how will you actually tell whether the site is operating properly or not. We're using a system called Signos for collecting several different types of things for monitoring purposes. And this is certainly not the only option. If I was working with a client that would let us use software as a service, I would probably look for something that I could pay somebody to handle running all of these dashboards and things. But Signos is an open source system, and it handles several different things: logs, metrics, and tracing, which I'll talk about here. So we've decided to use it for this case. So logs are always useful to see what's happening in your system. The problem when you've got a distributed system is you've got a bunch of different log files happening in different places, and it becomes much harder to find the right information at the right time. So you want a system that can do log aggregation. With Signos, we run as part of our swarm a collector that runs on every machine, automatically listens to the logs from every Docker container on that machine, and forwards it to a central location. Then it gets indexed, and we can query it and see what things have been happening recently. I won't spend much more time on logs because there's something else that's more useful, which I'll get to in a second. We also have metrics. Metric is a number that you measure over time, and then you can put it in a chart. Just as an example of a metric that I found really useful when looking at this site, we have this dashboard of what's happening in traffic, so the first layer of the system that traffic comes into. So we have a graph of requests per minute. I can easily see, Most of the requests are 200. That looks good. We have a graph of average duration, so I can see how long the requests are taking. If we're experiencing some difficulty or an outage, I'll come here and look to see, like, oh, are we getting a bunch of traffic? Is it suddenly taking longer for some reason? The graph in the bottom left is requests per minute by service. So the green line is varnish, which is what I want to see. I want most of the traffic to be coming from the cache and only occasionally going on to Plone. And then I've got a graph of open connections for each service. So if there was something down, like the database goes down and traffic is making it to the back end, but then just waiting for a connection to the database, then the requests are going to pile up and this line is going to spike. So it's an easy way to see when there are problems. Now, there's many other metrics. I would love to do more, for example, with metrics from the ZODB to see like how many objects are in the ZODB cache over time. We haven't gotten there yet, but can add it at some point. Distributed tracing is the thing I mentioned that I like better than logs. This requires instrumenting your application to record some more structured data about the requests that are happening. But in exchange for doing that extra work, you get something like this, where we've got the relationship between front-end services and back-end services, which are in blue. So we can see the top request came into the front end, and then it made several different requests to the back end. We can see how long they took. I can click on one to see some of the details about what path it was accessing. And then you can also instrument additional things. So I've added some instrumentation to catalog queries so that we can see how many queries happens for a certain request and what the parameters were for that query and that sort of thing. All this stuff is not that useful unless you actually have it tell you when something's wrong. So we've set up some notifications to Slack so that if there's a new error that we haven't seen in the past 24 hours, we get a message about it, and then we can go and see what's going on. We also have an alert for if the disk usage goes over a certain threshold, so we can find out, oh, we're adding too much data and need to increase the size of the disk. I mentioned Signos. That's what we're using for all of this. I won't talk about it more, but I do need to talk about the thing I'm using to do the instrumentation. So we need something that's running in the front-end process to record the requests that are happening and in ZOP to record the requests that are happening. There's a project called OpenTelemetry, which realized we've got all these tools like Datadog, New Relic, different services. They're trying to collect this sort of data from applications. Wouldn't it be nice if instead of having a different way to do that instrumentation for each of these tools, there was a standard way? That's what OpenTelemetry is. So there's a standard way to instrument a WSGI application for Python. There's a standard way to instrument Express for Node.js. So that's what we're using here. It all goes to a central collector, and then the collector can forward it to Signos in this case, but it could also forward it to Datadog or some external system in a different format if it needed to. Collective.OpenTelemetry is a package I've started, and to take the OpenTelemetry tools and integrate them into Plone to make it as easy as possible to set this up. Unfortunately, I haven't gotten to the point of making a release of it yet, but if you're interested in it, I'd love to talk about that and work a little bit more on the documentation and help you get it running. We're about out of time, so I will wrap it up and see if you have any questions.
Thanks, David. What do you have left in OpenTelemetry before you release it?
At the bare minimum, documentation. There's the actual way that you set it up right now is as WSGI middleware, which means you have to customize zope.ini. And I want to either make it easier to do that or use some monkey patching instead so that you don't have to do that. But that's more of a nice to have. Documentation is really the main blocker.
Thanks for the talk, it was very interesting. I also
Thank you.
have a bit of experience with Docker Swarm. We are using at least at one project and some smaller ones. And what I have heard in the last years is that the development of Swarm has stalled and Docker Swarm is dead. I hope it's not. And
I think that the development has stalled, or at least slowed down. I haven't seen evidence of a lot happening. It seems to be stable enough to be working for what we need. I wouldn't call it dead, but yeah, I think that's something to pay attention to. I think that there are people who are promoting other things instead of Swarm. I don't know that those people have the final say in what wins.
the nice thing with Swarm is that it's much more easy to understand than Kubernetes, as far as I know it. And the other question I have is, you were mentioning that you have history support enabled and hundreds of editors. I have heard again, without experience, that if you turn off the history support with multiple concurrent edits, that the site performs much better, right?
Yeah, I haven't explored the performance considerations, and that might be worth doing. The thing is, though, if you've got lots of editors, it increases the need to be able to look at the transaction log and see who broke the front page, right? So we're a little bit hesitant to completely remove the history. Maybe there's some other way to get it, though, like turn off history at the ZODB level, but record some other log of what's happening.
That was amazing. Thank you very much. I had a few, but I'm going to just stop at the Signa. Oh, wait. Actually, the ZODB cache size. That was an interesting thing you just touched on there and then moved pretty fast away from it. So I'm going to take this opportunity to learn here. You talked about indexing, the ZODB cache size having an index, and that made me ask to myself, what's in the ZODB cache? Is it an index or get cached? The brains get cached?
Any object that gets loaded from the ZODB gets cached.
There's the index.
And some of the objects that are loaded from the ZODB are the internal structures of the Z catalog. And those tend to be fairly important ones because every page you're loading is doing lots of queries and accessing those indexes. So you want those to be in the cache, which means that you want to have a large enough cache to hold them.
So the ZODB cache doesn't spend any special treatment between an index and a brain and an object?
No.
Well, that's sad.
Yeah, and in fact, I went down the path many years ago of trying to separate out the catalog from the rest of my site into separate ZODB storages so that I could configure the cache size separately. And that's how I got myself POS key errors, so don't do that.
Any more? Yeah.
So do you have a solution for secrets? So I saw you had the rel storage password there. Presumably you don't want that in your repository.
Let's just say, well, we could be handling that better. There are several things that are making sure that it's not publicly available, but yeah, we should think about that.
Like David introduced, I know a little bit more about this because I think I'm the service delivery manager for this thingy here. To comment on some things very quickly, Docker Swarm, yes, the first implementation of Docker Swarm 5, 6, 7 years ago is totally dead. But Docker Swarm is now like an integral part of Docker machine. It's just you enable it. You can enable it on your machine as a one single instance.
Yeah, that's a good point. Docker Swarm used to be a separate tool. Now it's just a feature of Docker.
Yeah, so it's there. I mean, Docker is a commercial company. If you look at their website, then Docker Swarm is kind of a bit hidden there now. But it's an integral part of Docker machine. Second part, secrets, you can manage those in CI/CD. You could also manage them in Docker themselves. Docker itself has a secret service now, just like you can do it in console or in other applications there. So that's there. That's totally hidden. So that's I don't know if David showed it in there, but you can we inject those from a totally different part, and it's totally you can do that very safely.
Thanks, Fred. Anyone else?
Yep.
It's not actually a question. I'm going to make an invitation. Yeah, sorry. I'm going to make an invitation for whoever wants to work on improving the cookie cutter that we have to also generate like a stack with varnish and Porger and so on. Join us during the sprints. Because even though every case is a little bit different, deploying a small site with varnish goes a long way in terms of performance. So we'll be available during the sprint.
Are you also tracing, logging stack traces, like with Sentry for backend and for frontend?
No. It would be nice to do it for the front end. I haven't spent time trying to figure that out. I'm sure it's possible. One thing that doesn't, it's not quite as nice as Sentry, where Sentry gives you this error happened now and this error happened now, and I can scroll back through other occurrences of the same error. This system is well, no, we do have that. We do have that. It's just a little bit less well tied to the alert. So we get an alert that says this error happened, and then we have to go dig around the system and find it. There isn't a direct link, but that's partly just a detail that we haven't worked out. But yeah, the main question was about front end stuff, and we've instrumented the front end to know what requests are happening, and I think we're not instrumenting the browser side. When I say we're instrumenting the front end, I mean we're instrumenting the Volto server, but we're not actually running something in the user's browser to detect when something fails. And that could probably be added, but then you need to figure out how to send it back to the server and the monitoring system and all of that.
Okay, thank you, David. Now we have a 15 minutes break for coffee.